Good afternoon, everybody. Thank you very much for being here. My name is Youssouf Traoré. I will be your master of ceremony today. We are going to talk about a little bit of AI, quantum technologies. We are lucky enough to have representative of this field with us. We are going first to start by a keynote speaker that is a friend of mine, Mike Grandinetti, and he's talking from the US right now. And Mike, for the people who don't know him, he is a serial entrepreneur. He's a teacher in Harvard, Babson. He raised like almost 1 billion euros for all the companies that he was in, CXO for all those companies. Is really someone that can, with his experience, can give us a glimpse of what is innovation, technology, entrepreneurship. So without further ado, I will ask you to welcome Mike. Mike, the floor is yours.
Youssouf, thank you. And I'm assuming we're recording at this point. Is that right?
We are recording.
Beautiful. All right. Well, first of all, I just want to thank Youssouf for the opportunity to spend a little time with you. I've got about 15 or 20 minutes, and really the purpose here is to set the context for the event to come. And I wanted to make sure that we really understood history, because there's no question that quantum has been on a long trajectory. And we all know it will be profoundly transformative. But I think there's a lot that we can learn from history in terms of the way that quantum's journey will continue to evolve over time. So let's just very quickly take a look at this infographic, right? And let's all recognize that as a human race, over the last 350 years, we have lived through what is now the 6th industrial revolution. And I know that may be a little bit inconsistent with what the World Economic Forum has described as Industry 4.0, but I think that this graphic provides a little bit more granular detail. And I think there's a handful of things I'd like you to take away from this chart before we move forward. The first is that for each wave of innovation, each of them were driven by a very small number of both innovations and inventions, scientific and engineering based. The second thing I want you to understand is that if you look at the horizontal axis, you look at the length of each wave. And so the first wave, which was really the beginning of industrialization, which was driven by water power and iron and textiles, where we really started to move from an agrarian society to an urban society. That was a 60-year arc. If we fast forward to the 5th wave, the digital era, that was a 30-year arc. So we're seeing a dramatic level of compression in the length of each wave. The second thing that I think is important to understand is the slope of the curve, right? So with each successive wave, the rate of change accelerates, it increases. That is because we are standing on the shoulders of all of the great innovators that have come before us. And so as we move into the 6th wave, and we certainly are in the 6th wave, I think there's a lot to be learned about where we're going to head. So let me just highlight one specific invention that has really changed all of our lives, and that would be the invention of the internal combustion engine. And then I'm going to draw analogies to the way that AI has evolved, because I think there's a lot of analogies between how AI and quantum are evolving. So let's go back to a typical street scene. It could be Madrid, it could be Paris, London, New York, in the late 1880s, okay? Horses and buggies were everywhere, okay? And the internal combustion engine, there's, success is always has many fathers, but there's 3 or 4 people that are credited with the invention of the internal combustion engine. But what's important to understand is that the very first patent for a gas turbine went all the way back to 1791. and the internal combustion engine was created almost a century later. So it took 100 years to get here. And then Carl Benz, along with Otto Daimler, the two founders of the company we now know as Mercedes-Benz, are both credited with coming up with the first gas-powered practical automobile in the mid to late 1880s, okay? So the first real practical application. And out of, in a very short period of time, we saw the internal combustion driven automobile being sold across the world, beginning in 1888 in Mannheim, Germany, moving to Detroit with a company that no longer exists, but one of the early automakers, Winton Motors, and then off to Osaka, Japan, with the automaker at the time, Yamaha, okay? And for a long, long time, we saw these two, quote unquote, technologies, the horse-drawn buggy and the automobile, coexisting peacefully on roads. But what really changed everything was the fact that when Henry Ford created the River Rouge plant, and he brought with him the assembly line techniques that allowed for mass production and a dramatic decline in cost, while at the same time paying workers enough that they all could afford to buy a car, everything changed. Now, even with that, it took 71 years to reach 100 million cars sold in the United States. We start with the Henry Ford quadricycle, which looks very much like the vehicles that were created by Daimler and Benz. And in 1967, we hit that 100 million car sold milestone in the US. And here I'm showing classic Detroit muscle. This is a 1967 Ford Shelby Cobra GT 500, just an absolute masterpiece of a vehicle, right? 100 years, recognizing that the gas turbine again was patented in 1791. Okay, so it's a very, very long evolution. And so what we learned from this, okay, is that, the inventors back in the late 1800s could never have conceived of the economic changes, the societal changes, the cultural changes. The automobile has changed everything about life today. And of course, we're on the precipice of another sea change in the auto industry with battery electric vehicles, right? So a new cycle has started and we're in the very early innings. And so what's very important to understand is that Roy Amara coined Amara's law. And this has held true for centuries, right? We tend to overestimate the effect of a technology in the short run, and we dramatically underestimate the effect in the long run. So now if we go to the next innovation cycle, which is the digital cycle, we look at what was really the true beginning of the digital age, which was the introduction of the Intel 8088 microprocessor in 1979, okay? And the beginning of Moore's Law that to this day, of course, is still relevant, although it is beginning to lose its currency. And so if you look at both the microprocessor, and here is a very, very early graphical user interface that Steve Jobs first saw in the Xerox Palo Alto Research Center in Silicon Valley, California. In the late 1970s, he saw this point of convergence, which led to him being a pioneer in the client-server revolution. And what he said at the time is a computer to me is a tool that we have to come up with. It's the equivalent of a bicycle for our minds. Interestingly, a lot of people are calling generative AI a tandem bicycle that we ride alongside of with our augmented reality friend who is providing us with a lot of guidance. And so Jobs was able to then bring the microprocessor in the Xerox PARC graphical user interface into the Lisa computer named after his daughter. And this was launched in 1983, okay? And here then is the graphical user interface of the Lisa. It looks mysteriously a lot like the Xerox PARC interface. And so what we've seen with all of these profound innovations, whether it be the mass production of the automobile, whether it be the introduction of a computer with a graphical user interface, is the fact that great entrepreneurs were able to democratize these inventions, to make them readily accessible to the masses. And of course, we saw that again with the introduction of the iPhone. And the simple analysis that Jobs showed on stage during the very first Steve keynote, where he talked about the fact that there were a lot of what he called usual suspects that were hard to use and that weren't very smart. And he identified this huge blue ocean in the upper right-hand quadrant. And he delivered on that promise in such an effective way that 2.5 billion iPhones have been sold, and we're still counting, okay? And so, the iPhone, along with the App Store, which was really the killer app, felt like magic, right? It changed everything about our lives. And, we've been living through this digital transformation now for the last 35 or 40 years, but we're just getting started. And now I want to talk about AI and how it may foreshadow what we might see in quantum. Now, you probably all know that Alan Turing proposed something called the Turing test as far back as 1950. But artificial intelligence really was born around 1955, 1956 at a conference at Dartmouth College, an Ivy League university up in New Hampshire. And there's been a very, very long gestation period. And you'll see here this thing called the AI winter, where there were many false starts. And of course, there have been some significant milestones that we've achieved. Now, I was at UCal Berkeley last week with one of the great minds in artificial intelligence, Dr. Peter Adil. And Peter has been involved in a lot of sort of seminal innovations around AI. And I love this somewhat tongue-in-cheek timeline that he put up. He said between 1956 and 2012, not much was working within AI. But after Professor Geoffrey Hinton, who at the time was working at the University of Toronto, was able to prove out the value of deep learning, on something called AlexNet, and where the more data that you had, the better that the system worked, the better, everything began to change. And this is just a photo of Dr. Adil, who's now heading up a very, very forward-looking robotics company, okay? And so the second thing that Adil said, also tongue-in-cheek, is this was the life of an academic before 2012. Very boring. I just spent a lot of time doing research and working on papers and reading. And after 2012, I'm being invited to dinners with Jeff Bezos and Bill Gates to talk about AI. So there was this huge inflection point, right? And so let's fast forward. And all of a sudden, beginning in about 2015, we started to see a number of skills begin to match and then quickly surpass human performance, from image recognition in 2015 to speech recognition in 2017 to reading recognition and comprehension and handwriting recognition in 2018, and more recently.
Could you try again?
And so, of course, we all know now that there was a killer app that was introduced almost a year ago to the day. Okay, and that killer app, as we all know, is known as ChatGPT. And I imagine many of you saw some of the profoundly interesting announcements that came out of what was Dev Day just a week ago Monday, okay? And again, what we've seen in this new world order is, once again, the democratization of these incredible inventions, in this case, natural language processing. You can now type into a text box, you can talk into ChatGPT, you can take an image and upload it, you can upload a PDF and summarize it, right? So all of a sudden, we're able to access AI without the benefit of a data scientist, okay? But it's only the tip of the iceberg, of course. And there are so many companies that they heard the shot across the bow, right? This was the shot across the world, right? As soon as OpenAI released ChatGPT, we saw Cohere release their LLM, Amazon released their models, Meta released Llama, Salesforce.com announced Einstein, ChatGPT then upped the game with GPT-4, which is what we're working with today. And we continue to see Anthropic and Microsoft and Google all make significant announcements all over a period of about 4 months. So it's really accelerating. And not surprisingly, this created a Cambrian explosion of startup activity, application development, and why? Because what's interesting about ChatGPT specifically and generative AI in general is that although the hype is unprecedented, the number of real use cases to solve real business problems and coding problems today is almost limitless. And so this is a very unique period in time where, yes, there's a lot of hype, but unlike Web 3.0 or virtual reality or a lot of the other highly overhyped technologies that never really had a killer use case or a killer app, Gen AI is very, very different than that. And there's a dramatic level of adoption, right? And so remember, I said it took 71 years for the US to buy their first 100 million cars. And I realized that it's very different to buy a car than it is to download an app. But it took 2 months for ChatGPT to get to 100 million users. They talked about the fact now that they're seeing 100 million users a week, about 1.5 million visitors every month to their website. Okay. And so we are absolutely living in the age of AI. And to deny this would be similar to denying that we're living through climate change. It just would be hard to intellectually make any argument to the counter. And just because of the nature of this audience, I wanted to share one use case with you. What you're looking at here is the conference room of one of the most successful life sciences venture capital funds in the world, Flagship Pioneering. You're looking out at the Longfellow Bridge off the MIT campus. And Flagship is responsible for, amongst many, many innovations, the Moderna COVID vaccine. And they are leaning heavily into generative AI, right? They're building technologies that will allow them to sift through massive quantities of scientific data and literature so that they can identify opportunities where they believe a new successful startup can be created. And they are a venture studio, right? So they don't go out and take pitches from founders. They actually come up with their own belief system, their own investment thesis based on this kind of work. And then they go out and recruit the appropriate founding team. And once they fund these companies, they're now helping them with a huge number of computational challenges, right? As they want to look for all kinds of different insights from huge data sets. And this is obviously an area where I think quantum computing will be invaluable as we evolve over time. Now, what they've obviously needed to do here, because of the nature of the application, is they needed to focus on accuracy. So they will be able to provide you with sources, right? 15 papers that informed the results of this search, okay? And so the message then is the future is already here. It's not evenly distributed. And many of you are either in Spain or in Europe, and you'll notice that no European country is on the list of the top 5 users of ChatGPT, at least not yet. And I was surprised to see that Colombia and Brazil were ahead of some European countries, but that's just the way it is right now, okay? And so if we look at the hype cycle for generative AI, it's very interesting because it's unlike any hype cycle I've seen before. A lot of these applications at the top of the hype cycle are actually very, very useful. In the words of Gartner, right? They've reached the plateau of productivity long before their models would normally say they would, okay? And so as I begin to wrap up my remarks, right, let's talk just very quickly about quantum computing, and I am no expert, but I think let history be our guide, right? We saw a number of key milestones, and what I find really interesting is the polymath, Dr. Feynman, Richard Feynman, who was a professor for many years at Caltech, probably one of the greatest minds of the 20th century, proposed the idea of a quantum computing platform all the way back in 1961. That is only 5 years after we saw the Dartmouth conference on AI. So the evolution of both of these things has been tracking, over the same cycle fairly closely, right? And a handful of milestones from Shor's algorithm in 94 to the first quantum computing prototype going all the way back to 1998 that was created by IBM and Stanford. They finally were able to demo Shor's algorithm. The concept of quantum supremacy came up in 2007, and then Google's quantum supremacy with their quantum computer qubit Sycamore in 2019. So there's clearly been a huge number of important milestones, and now we're seeing a lot of scaling going on, right? And what's interesting is that when you look at Gartner's most recent hype cycle for emerging technology, quantum computing, specifically for cryptography, is the initial use case that they target here. I would have expected to see more than that, but that's just, Gartner, who is very much a client-centric company, and they're obviously not dealing with research labs. They're dealing with, traditional enterprises. So there's a number of different use cases that appear to be ideally suited for quantum computing, okay, across a number of industries. And the question becomes, what will be the killer use case that will drive adoption? What will be the killer app that will drive adoption, where there's a target segment, there's a burning problem, and where the quantum computing platform delivers a profoundly important differential advantage? So that's really all I have, Yusuf. I hope that was helpful to maybe set the tone.
Thank you
for
very
the
much.
discussion to be had.
Thank you, Mike, for setting the stage for quantum computing. We saw that AI was one of the technology that is going to change our world, and quantum. And we'll see now with our guest here what quantum computing means, how we can have an impact direct in our life, and we will Mike exactly this one. Mike mentioned the quantum use case, computing use case that we are lucky enough to have with us today. Antonio, that will show us live what are the use case that can be done today in quantum computing. So join me for a round of applause for Mike. Thank you, Mike, for your presentation.
Thank you, Yusuf. I wish you all a great rest of conference today.
All right.
Take care.
Please have a seat. So now that we have set the stage with AI and the disruption that we are facing, let me introduce you to our three guests that we are lucky to have those experts with us. I will start by the distance. We are with Houston. We have a problem today. No, it's Juan Moreno is in Houston. He's working for Amazon.
Close enough.
Amazon Web Services. It will show us today what Amazon is doing in terms of quantum computing and how quantum computing can help us in logistics, because it's one of the area that it will solve a lot of issues. We also have with us a former colleague from BBVA, Antonio. Is a quant by definition, by formation. He went to create his company with this called Centroid with Carlos Krzyzewski, that is a co-founder of Centroid, a professional that he has a background, a technical background, but thankfully today he will be able to to distill what is exactly quantum computing, because the idea of this event was to have experts, but also people that don't know anything about quantum computing to understand what it is. And my objective at the end of this event is you guys getting out with to know what is quantum computing and how it can help you in the near future. If I succeed to that, I will be happy. And then last but not least, Alvaro, that is working in BBVA, in the team that is in charge of the quantum technology. So it's another area, the finance, that is that will take real advantage of the powerful the power of computation of quantum computing. So please join me to welcome all those three panelists. So I will start by Houston. My first question is, computing is a great topic today. So could you explain in simple terms, what quantum computing is and how it differs from classical computing? Because we all have computers from a very long time. So how would you define and differentiate it from the classical one? And then I will
classical computers. Yeah,
I will pass
sure.
the mic to people here. Please go ahead, Juan.
Excellent. Well, very nice to meet you all. Thank you for having me. I'm close enough to Houston. I'm in Austin, so it's just 3 hours drive. But no, we don't have a problem so far in Houston up until now, neither in Austin. So all good here.
Perfect.
It's I'm gonna try to explain what quantum computing is for the layperson. As you know, it's a complex topic, but as also Feynman used to say, if you are not able to explain it for someone who is in, let's say, in high school level, that means that you don't understand it yourself. So I'm gonna try to follow his lead and try to explain it to you. But basically, quantum computing is a new paradigm for computation, and it's leveraging the laws of quantum physics to work. And what that means is that it doesn't follow the classical physics, in which we had binary systems to build the computers. So a classical computer is full of transistors. It's based on the transistor, right? And a transistor is a very simple device that can take two values, 1 or 0. When there is a 2-volt electricity current or something like that in the transistor, you read a 1, and when there is no electricity on it, you read a 0. And when you put trillions of those transistors together, as we have nowadays in our laptops or even our phones, then you are able to perform calculations at a very fast speed. This is polynomial or linear speed. As you add more capabilities, more of those transistors, that translates into memories, into CPUs, into all the terms of classical computing that we are familiar with. That's good and all, but the main difference with the quantum computers leveraging those laws of quantum mechanics is that we have a new system that also can take two values, 1s and 0s, but instead of depending on electric currents, it depends on the quantum states of generally subatomic particles. It can be a photon, it can be an electron, it can be an ion, a part of an atom. And depending on how you manipulate the state of that quantum system, you will be able to read a 1 or a 0. Obviously, as you can imagine, this is an engineering challenge, not only a scientific challenge, but also an engineering challenge to get the readings that we want from these devices. And on top of that, they have the added functionality that since they work differently to the classical physics, these particles can take what is called a superposition of states, in which we can have the value of 1 and 0 in a superposition working simultaneously. And that simultaneously feature is what allows us to do certain calculations at a much higher efficiency than a classical computer. The first thing that we need to be very clear about is that not every problem can be translated into a quantum computer. It doesn't mean that we're going to be able to to have video conferences or write emails in more powerful computers. It means that there are certain types of problems that can be optimized when we use a quantum computer. And we are basically these days trying to find the best use cases for those quantum computers. Usually are problems that requires adds a lot of complexity when you add new variables to it. When you put one more variable, the complexity of your problem grows exponentially rather than polynomially to resolve. And that's where quantum computers really make a difference.
Okay, so basically what
we are trying to solve those new different problems with these machines, and they are difficult to build.
Okay, so you talked about the different state of the atoms. That's something that is totally new from the classical computing, and also the fact that you didn't mention the entanglement, but it's something that we will talk about a little bit later. Antonio, could you give us your simple definition of quantum computing and the difference? And then we'll ask Alvaro.
For me, quantum computing is from the difference between quantum and classical. It's the difference between algebra and logic. Classical computing is all about logic, all about logical gates, true, false, change in values, but it's deterministic. All the things that happens in your laptop or in your mobile are one or zeros only. Quantum computing is different because we introduce some kind of algebra, complex algebra. I mean complex because we use complex numbers. It's not all the maths below the process are not complex. Matrix multiplications and matrix aggregations, all the things that everyone can perform with a low level of math expertise. But the difference here is that quantum computing is not deterministic. You manipulate the probabilities to have 1 or 0, and you do with different kind of algebra tricks, but it's not deterministic. So if you want to have a result, you must run your circuit several times, because each time or each shot you will have some result, and the final result will be the distribution of probability or the distribution of result, and you need to have some kind of expertise to interpret that result.
So it's really complex. So it's not something that easy, like 1 or 0.
It's very complex.
The sum of different states. I try to resume for the people that I'm an engineer, but not everybody is an engineer here. So I want to make sure that everybody understands. So it's a sum of probability that makes the result. So to say it on a simple way. Alvaro, what do you think about quantum computing? What is your take?
So what I would say now is things are quantum in a sense that atoms are quantum, electrons are quantum.
Nature
is quantum in a sense that insulators, for instance, insulators are insulators because of quantum properties. Metals are metals because of quantum properties, and so on and so forth. The important thing in quantum computing is that information as well is quantum. You're using quantum information, right? Which is what we were talking about before. We were saying that we have bits. These bits can be 0 or 1. These are binary quantities. Just binary means 2. And in quantum computing, you use qubits, which are this kind of big cousin, if you like, of these bits, right? They can be in a combination of 0 and 1, which is what one was calling superposition. And they also have this strange property of being entangled. They can also have this, they are so-called very strong correlations. Okay, just to imagine what it means. Okay, imagine that you have two quantum particles, two electrons. You shoot them apart in space. Okay, one goes to the Milky Way, one goes to Andromeda, whatever, and they are entangled. If you measure one of those qubits, then the other one immediately assumes a given state, right? So this is a correlation that is much stronger than you would get in any classical setting. That's something that quantum has.
Let's make sure that everybody understood that it's two atoms that are linked. Entangled is a fancy word to say linked. So they are linked. And imagine you take a ship and you go to Mars. And with those, one of the two atoms is in Mars and the other one is here. When you move the atom here, the other one is moving too. So basically, it's the base of communication between in space. So if you are sure to have an impact, and to know what impact will have the other atom in your place, you're able to communicate. So this is entanglement. This is one of the property of quantum, and this is the power of quantum. But we have many other things. So let's keep going, please.
Oh no, that's I would add also maybe quantum interference, but I believe it like that.
What about superpositions? What could you? Superposition is another property of quantum. Could you give us a?
So superposition just means that instead of being just 0 or 1, you are in a combination of those two, right? With certain probability of being in 0 or with certain probability of being in 1. This means that you have sort of an infinite amount of possibilities where your state could be. This doesn't mean that you are going to measure that. Every time you measure your qubit, it's going to be a 0 or a 1 with that given probability. So that is superposition, and then you can get superposition with a lot more qubits, and it gets a lot more involved, right? That's where the exponential properties of this kind of things arise.
And this property means that you are capable of having problems that we couldn't solve before, because the dimensions of the problems when we gave those type of problems to a computer, a classical computer, they were not capable to do it, or it would take really a long time to be able to solve that. But with property, with the complexity of the equation, something that can be solved. So Juan, I have a question for you. It's about the encryption, the quantum encryption, because encryption and security are two domains that are really important when you use quantum communication. How is quantum addressing those problems, the challenge in data security?
Sure thing. So probably if we continue with the analogy of the quantum entanglement, that could be a very good way to address this question, right? So when we think that we have two particles that are spread apart in two distant locations, and modifying one is gonna modify or is correlated with the other one, we can think immediately, oh, if I put a series of many of those, I'm going to start to produce ones and zeros, very big strings of ones and zeros that are going to be correlated on both places. I could use an encryption key with that. And that's the first thing that comes into helping with encryption. A quantum helps with encryption. In quantum communication or in quantum cryptography, what we are doing is to use the properties of light, the properties of photons, to using the polarization or other features of the phase of these photons, create ones and zeros and create encryption keys with those properties. If we are able to encrypt our data using those keys, it doesn't matter that an attacker tries to hack into my link and read my information. As soon as they try to read my link, that's going to be considered a measurement, and immediately it's going to destroy the properties, the quantum properties of the link, because you are trying to read it, and the communication will be interrupted if you implement it correctly. That is one immediate, simple way in which quantum communications are helping to protect the cryptography of the future.
And in BBVA, is there anything that I know that JP Morgan has implemented some the communication, quantum communication between branches, some branches, and they have a network. JP Morgan is one of the banks that are usually at the forefront of the technology, but BBVA too. So could you tell us anything that BBVA did on that?
Yes, so BBVA was involved in a project of quantum key distribution, which is what Juan was talking about, is with sending sort of keys. Okay, these keys are used for encrypting messages via satellite and using it via quantum protocol. Okay, that's one of the things they did because I wasn't there at the time. But maybe the most interesting thing I would say in the quantum part related to cryptography is that companies right now, such as ours, they have to start doing an inventory of what crypto systems they have and everything. Because even when the protocols change to something that can be robust against cryptography, you need to find the areas that are sensible to those and change the protocol accordingly. So that is a job that has to be done before there is a breaking of classical cryptography. And that is one of the areas where BBVA is right now involved.
Interesting that you mentioned the fact that you have to change the type of cryptography that you have, because there is a new fashion now that people store the data now of all the transaction. They cannot decrypt it because they don't have the key, but they store it to be able, when the quantum computer will be there, to decrypt it because the information will be still relevant. So it's why a lot of sensitive information by those company banks, and they are changing right now all what they have to be able to be quantum safe. Antonio, in Q-Centroid, do you have any protocol that can be used to, or that a client came to you and said, could you help us on that, or anything like that happened with your clients?
Well, our business model is not about quantum cryptography, but we have some researchers that are working on quantum cryptography. We say that cryptography algorithm is safe if you cannot break until the end of the information. If imagine, for example, that you have some bank transactions and probably 100 years after now, that those transactions has no importance. So if you cannot break the current security algorithm, cryptography algorithm in less than 100, that algorithm will be unsafe. If not, will be safe.
Okay.
We are working to develop different kind of, not cryptography algorithm, some kind of algorithms that tries to work with neural networks to discover new ways to implement that secure algorithm. Because now the problem is that, okay, there are a lot of different proposals, but now there are no standard post-quantum cryptography algorithm. We have to develop different prototypes. We have to test everything, and after that we will have an standard. Now we don't have, so we are trying to help the industry with our neural networks to discover new points of unsafe or new different breaks with some kind of AI motors or something like that.
So AI can help you, and
Yeah.
actually it's the case. I was last week in an event on quantum computing, and there was something that was said there that I like is where AI starts quantum, and AI can help a lot of algorithm in because it's powerful to do, for example, in terms when you have interference to reduce the noise. This is one point, but you are talking about the challenges. This is one of the challenges that quantum computing has. Do you see any other challenges that is relevant, because it's at early stage for the past 10 years now we are talking about quantum computing. Do you see any other challenges for quantum computing? Alvaro.
So quantum computing right now has many challenges. On the development side, it has a lot of challenges, right? It's an engineering problem that you have to solve. You have to solve problems of scalability. Right now, you are talking about 1,000 qubits or so, just to give you an idea. That is a very small number, okay? And if you wanted to break these encryption systems, you would need around 1 million qubits or more that were working perfectly or something, right? So those things are something that have to be solved. As well, on the algorithmic side, you also need to address that point, right? Because there are algorithms right now, quantum algorithms, that are better than classical algorithms, right? Especially for the case of encryption. But for other applications, such as financial applications, there are quantum algorithms which offer an advantage, but it's not a huge advantage, okay? And we still need to work, which is why this point in time is quite interesting, because there is a lot of work to do still to find the best algorithms for when these machines are ready. So there are many challenges ahead. These two, I would say, are probably, at least that's what I see, the most relevant.
Okay, Juan, do you see any other challenges?
Yeah, it's directly on the lines that you guys are discussing, right? Alvaro was talking about optimization problems, probably, that are very relevant for the financial industry, the finance sector. And related to that scalability problem that he was mentioning, comes the noise, right? The reason why it's so hard to scale these devices is because they are unstable. These quantum states only last for a few microseconds, a millisecond if we are lucky, right? The way to keep those systems, quantum states, alive and long lasting to do calculations is one of the main challenges of this industry. Right now, you build logical qubits. Basically, it's like cluster a lot of physical qubits together, knowing that they are going to fail or they are not going to land in the state that you expected to produce one good qubit. For that reason, to build a machine with millions of effective qubits, you probably will need hundreds of thousands of millions of qubits to achieve those perfect qubits, right? So noise is one of the engineering challenges. And depending on the implementation of the quantum device that we are talking about, we will be referring to radiation from the Wi-Fi signals that are nearby, or even dark matter in the universe that is affecting your quantum device. And the most popular one, those huge candelabra that you see in the fancy pictures of quantum computers, make them as cold as possible so the particles don't move while you are doing the calculation.
You are mentioning the hardware problems. What could you explain us what development we had in the hardware and the quantum processor and the scalability? Do you have any information about that part of the quantum computing? Juan, maybe you want to.
Yeah, I know a few of the platforms. In AWS, we are working on a superconducting loops device. That basically means a very, very cold metallic plate that will be used with electromagnetic currents to produce those ones and zeros that we were discussing at the beginning.
Just to
That's
make sure,
just one of the technologies.
just cold because the heat makes the electrons moving, and then you have noise. So it's why you need to cool as much as possible. Am I right?
In the case of superconducting loops, you are totally right. You need to give them at least a minus 273 degrees Celsius in order to create that superconductivity that those metals show at that type of temperatures. And as you say, the electrons stay still for me to do calculations.
Okay.
Then we have other platforms like the trapped ions, for example, in which you get a standard atom, as we know it from the high school. You remove one electron on the outer layer, and then that gets charged positively, right? And that's an ion. So you can use those ions as well to create calculations. In that sense, your challenge is going to be to put that ion in a vacuum so it doesn't get affected by anything outside. And you point up until 6 lasers coming from different directions to hold that ion in place, and then combining those lasers, removing here one, adding another one there, start making that particle to rotate in order to execute the gates and the calculations and produce those ones and zeros. That's just another example of how a quantum computer works, but there are up to 7 different designs as far as I know.
Wow.
And most of them require very low temperatures. Not all of them, but most of them.
Antonio, you guys are more software, but do you have any hardware issues that you want to mention with us, or Centroid is more on the software part?
Well, here in the problem is that quantum computing or quantum computers are has a very low availability. So, for example, if you want, there are a lot of different quantum resources that are free to use. A lot. You can ask IBM, you can ask the Wave, and there are a lot. But the problem is, for example, if you are going to IBM and you want to use a free quantum computer, probably you have to wait like 3-4 days, 2 weeks, 1 month to see your circuit computed, and probably your circuit has to run in less than 1 or 2 seconds, but you have to wait 2 weeks, 1 month to see your calculation completed, and that is one of our problems. And on the other hand, if you want to have a paid hardware, you have to spend not so much, but you will have some problems because you won't have ever a quantum computer in your company. You have to pay per use, some kind of Amazon or Microsoft, Google. There are a lot, but you have to pay. You have to wait, and when it's your turn, you send your circuit and you have the calculation completed. If you want to buy a quantum computer, probably you have to spend out of money.
How many? 20 million, something like that?
Well, not so much.
Really?
For business applications, probably more than 100 million. But you could buy now some quantum computers with 1 or 2 qubits only for educational purpose, and you will pay no more than 6,000 euros or 9,000 euros, depends on the model.
Okay. Or use Centroid.
Or use our platform and
it's way
save
cheaper.
a lot of money.
So yes, Alvaro, you want to add something?
Well, yes. So if I adding on what Juan was saying, there are a lot of different platforms, right? And because of this competition between different proposals, things are evolving not that slowly, and advancements come up very, very quickly from different providers. It's also true that one who has to take them with a pinch of salt and see how good are the qubits, etc. But one of the proposals that IBM has introduced, which is interesting, is what they call this quantum supercomputing quantum centric. Okay, so it means that you have different quantum computers and you connect them via quantum communications or via classical communications, and that would allow you for a more flexible platform and more scalability. And they believe that they will achieve around 20,000, 100,000 qubits in a short period of time following that strategy. Because trying to achieve a full quantum computer with 100,000 qubits in the short term, that's, I would say, out of the question.
So I read recently that what IBM said in 2033, they would have 100,000 qubits. So it was using that technology, because it's a mixed, actually, basically it's a hybrid.
Yeah, it's a hybrid,
okay.
Yes.
Because right now what we have the most powerful is like 433.
433, yeah.
Yes.
Well, Atom Quantum, I think it was Atom. Yeah, they announced 1,000 qubit computer, but
okay. So in order to have a more complex and more powerful, you need to have hybrid computers.
Probably yes. In the meantime, yes.
So talking about the development on the hardware, could you do you have any development on the algorithm? Do you know anything that was done recently that makes the algorithm better or closer to reduce the noise? Is there any breakthrough? Juan, let's start by you. Is there any breakthrough in the algorithm?
There are new lattices that are being tried in terms of the topology of how the qubits are sorted on space in order to make the scalability more efficient. All those number of qubits sounds very fancy numbers when we say 100,000 qubits, 1,000 qubits, but if they have not good connectivity with each other, it's just a big orchestra making a lot of noise, and you're going to get just random results on your calculations. That's why number one, those hybrid options are very useful. In AWS, we have what is called the hybrid jobs, in which basically you are making cooperate classical computers or HPC resources with the quantum computer. But also in the engineering side, there are new advancements, at least for superconducting loops, on how the different qubits can be connected in 3D lattices that will allow better connectivity for those qubits and improving the results of your computations. At the end, what you need to look at is number one, coherence time for your gates that are durable, the gate fidelity, basically that you get what you expect when you do a calculation, and the qubit connectivity, as I was mentioning. Those are the three key factors, and there's no one single recipe that right now fixes the problem, and it depends on the hardware.
Okay, something that is really interesting, that I think is really interesting, is education. What is the state of the art in education in quantum? How many quantum computers engineers do we have in the room right now? And is there anything, if tomorrow my daughter that is 12 years old wants to be an engineer in quantum computing, is there anything that is set for her, or what can she do, or what can the young people here do to have more knowledge in quantum computing, be the next engineer in quantum computing?
Okay, so right now, the interesting thing about quantum computing is that you don't need to have a PhD in quantum computing, which is great.
It's good.
Because, I mean, if you want to develop the quantum computers, then probably you need a PhD in quantum computing, right? But if you want to just program quantum computers, then maybe it's not necessary. And right now there are masters in quantum computing. I teach myself at one of them at the Universidad de Nebrija.
You should do the promotion.
But there are also many free resources online. IBM offers a lot of open courses online, because what happens right now is that a lot of they need more people than they can hire, right? So they need this widespread adoption, and they are offering this knowledge for free, right? So if you search, for instance, online, you search IBM Quantum, for instance, you are going to find a lot of resources on that site. And there are many. Right now, the internet is full of resources to learn quantum computing, I would say. So if your daughter wants to learn quantum computing, of course, she has to learn maths and she has to learn programming.
Okay.
You don't really need to learn a lot of physics. Okay, I'm a physicist by training, and I have a PhD in physics, so I shouldn't be saying this, but maths and programming is essential.
Antonio, you confirm that you guys are looking for hire people because it's really hard to find, right? So it's the future, guys. If you want to have a job, you need to go on the quantum side. Could you tell us, Antonio?
Here in Spain, we have a joke that is that we have a quantum Spanish mafia, because if you look at almost every big technological company, big like Google, Microsoft, and Amazon, and more, and you see who is the responsible of the quantum development in that company is a Spanish guy.
It's true. It's true.
It's incredible. The father of the quantum computing, apart from Feynman, that is in the 60s, is a guy from the CERN in Switzerland. That is Ignacio Cirac. Is probably the next Spanish Nobel Prize I think in 2 or 3 years. And he is the father of the quantum computing, not the quantum maths or the quantum physics, is the father of the quantum computing. So here in Spain, we have different options. There are a lot of startups that are using quantum. We have probably the biggest startup, European quantum startup that is called Multiverse. That is one of our partners. We have a very good relation with them. In Barcelona, there are a lot of companies that are quantum companies, like, for example, Kilimanjaro, that has won the contract to build a quantum computer in the Barcelona Supercomputing Center. In Galicia, we have CESGA, that is a public institution that are trying to build another quantum computer in Galicia. In Basque Country, we have different options to work in. We have a lot of startups, Spanish startups to work. If you want to study, I will recommend you, of course, the University of Barcelona has, I think that they have the best quantum program, but also in the Basque Country, the public university in the Basque Country, here in Madrid, also in the south of Spain, we have a lot of universities, public and private, that offers you different quantum. I will become a teacher in one of that universities, so there are a lot of options, but you don't need to know about quantum mechanics, quantum physics. I don't know anything about quantum physics.
No, don't say that. Don't say that. They see you as an expert. No, you shouldn't.
I know how to program circuits. I know how to develop algorithms, and I know how to integrate those algorithms in different business. I know use cases of every kind of industry. I don't need to know anything about. Okay, I know how this computer works, of course, but I don't need that. I don't need that. If you want to develop an algorithm, go to the free courses of IBM, for example, or Amazon also has free resources to start learning, and you could start developing your own algorithms in 2, 3, 4 weeks, no more.
I think there is something that is constant with all those people that are working in quantum. They all say, I don't know anything about quantum. It's something that I have every time the same conversation with them. Yeah, but I don't know anything about. Guys, you know way more than anybody here.
Yeah, of course. But
so I had that conversation with him. He said exactly the same thing. Antonio is saying, no, I'm telling you, every time that you see someone that is working in quantum computing, he's saying, no, I don't know anything about quantum. No, this is not true. They know a lot. So, talking about the Spanish that are everywhere in the world, well, Juan is the good example of that in Austin. So you agree with Antonio that Spain is one of the best provider of resources in quantum?
100%. I talk to companies and academic institutions all over the world. Probably south of Europe, and particularly Spain, is one of the most active areas in both startups, enterprises, and academic resources, and universities with master programs. So yeah, on terms of the Spanish presence in the industry, a lot.
You did great.
Mentioned already a few companies. We have also Lux Quanta, for example, in Barcelona, that is building their own quantum key distribution device. We have companies like A Quantum in Madrid that do a single platform for all kinds of quantum devices to program circuits. So it's bursting really in Spain. And it is true that you don't need a lot of knowledge to get started if you are curious enough, right? My advice for people who are starting with this, and especially if they are young people that still have the whole life ahead to learn these things properly, would be following this dual approach. Yeah, start playing with things, break things, try to understand it. But I'm going to quote Feynman once again, that he used to say that there is a big difference between knowing the name of a thing and knowing the thing. Most of us that started with this, except people like Alvaro that has proper education on it, we have been learning when we were doing it, but we are too old already to learn all the fundamentals. And we just know the name of the thing and know how to use the language and build algorithms and all that stuff. But having a deep understanding on how things work by learning the linear algebra and the mathematical fundamentals of quantum mechanics will help you a lot to get a much broader understanding on the field. If I can just provide one resource that I particularly love, is a website called Quantum Computing for the Very Curious, that does exactly that, follows the whole journey. And if you are patient enough to follow it for 3 months, you will get all the basics that you need to start practicing and moving to all these websites that offer more practical approaches to build your first circuit and do more fancy things with quantum computers.
Juan, you don't see it. I'm doing a little bit of promotion for a friend of mine that I met in Puzzle X. It's the author of the Quantum Computing for Dummies. It's really interesting. You should, if you are looking for a book to learn basics of quantum computing. I don't have any money on that. It's just a friend of mine, so you guys should buy it. So I have a question about the other industry, because I would like to broaden a little bit. We talked about finance, but maybe in the example that we'll give you later on, because we'll have a demonstration, a demo on the platform of Q-Century to show you a little bit what are the industry, how quantum computing can shape the other industries, healthcare, for example. What do you think about that?
Quantum computing can help every industry in the world. For example, we have out of logistic clients that want to optimize their trucks in terms of routing, in terms of charging the trucks. We have energy companies that wants to optimize or predict. For example, they want to optimize the resources that they have, and they want to predict in a better way when or where they will have a peak of energy consumption. We have manufacturing companies or like food and beverage. We are trying to help them not in quantum computing, but in quantum simulation. Simulating different kind of, for example, we have a client that is a beer company, and they are trying to simulate the different behaviors of any kind of ingredients to put in the beer. And we are simulating them. For example, we have another use case that is very interesting, and we are going to publish very soon. That is quantum simulation to capture carbon in vehicles, simulating different metals or different materials to help the car to reduce the carbon emission, for example. So we can perform, for example, for simulation, we can perform millions of different combinations of different materials, different metals, different whatever, in seconds, in minutes. If you want to do that in a lab, probably you will need to hire thousands of people, and probably you will spend like 10, 15, 20 years to complete the experiment. But with quantum, if you know exactly what you are going to experiment, you could do that in minutes and hours.
I have the same example that you have on the beer company. I met last week an owner of a beer company, and he was saying that the expenses to produce beer were triplicating because they're using cereals, and you guess what? There is a war somewhere in Europe, and the origin of cereals is this place, the water that they are using. So he's counting a lot on quantum computing to reduce the way of combining all the different sources of the beer to have a good beer, but also to reduce all the excess that on the transformation process of the beer. They want to use quantum computing. So yes, it's something that is concerning them because their cost triplicate in 5 years. And if he was telling me if he wants to put the real price of a beer, it should be 15 to 20 euros a bottle. Nobody will buy a bottle of, not everybody will buy a bottle of beer at 15 or 20. So he needs drastically to find a way to reduce his cost, and quantum computing is one of that. So I would like to have another question. There is a term that is mentioned often, is quantum supremacy. Quantum supremacy, Michio Kaku, that is someone really known in the scientists, really known. wrote a book recently about quantum supremacy. First, could you explain to the people here, Alvaro, what is quantum supremacy and how it will impact us?
Okay, so quantum supremacy was a term that was coined by John Preskill. Preskill is one of the leading scientists in quantum computing all over the world. It turned out that the term wasn't very well chosen because it remembered of white supremacy and things like that in the US. And then it was changed to quantum advantage. But quantum supremacy really means that you can solve a problem faster with a quantum computer than with a classical computer, okay? You already have algorithms with demonstrated theoretical advantage, if you like, but the question is to run them on quantum hardware. And that was one of the things that Google did on 2019. It remains a little controversial if it is quantum supremacy because, well, there are other, they did an experiment where they solved the problem. It's a useless problem, okay? But they said that a classical computer would take the age of the universe, say, to solve it, okay? Then IBM came up and said, well, it's not the age of the universe, it's a couple of days and things like that, okay? And then, well, there's always this competition, right? Which is great, right? Because you can, it drives new methods to solve things because of this. And then there's quantum advantage. So quantum advantage is something that hasn't been achieved for sure. Okay, you can say quantum supremacy has been achieved or not, but quantum advantage hasn't. Quantum advantage is putting quantum computing to solve a practical, real problem, right? So a finance problem, a healthcare problem, a logistics problem, there's still no quantum no problem, no real use case that has been solved with quantum computer better than with classical computer.
I would challenge you on that because some companies that there is a startup that I'm following that, or a bank, succeeded into reducing the optimization of the portfolio, reducing drastically the amount of money that they would lose with the portfolio. So it's a real case, no?
But did they do it with a quantum computer? That was
it was Terra
quantum, yeah. I'd say that they did it with a quantum-inspired algorithm.
It's a hybrid. They are using a hybrid.
Okay, that's
a hybrid one.
That's the point. The question is, if you use a purely quantum computer, can you beat a classical computer? Right now, that hasn't been.
So definitely, we have.
You still need to leverage
power.
Yeah, you still need hybrid.
Right. And it's why hybrid is a solution. Juan, I see you. Do you want to add something on that?
Yeah, no, I was just nodding because it is true that you can use a quantum algorithm and run it on a simulator on a classical machine to achieve some speed up for some toy problem or reduce number of variables and make big claims about it. And that's what we see, unfortunately, in the industry quite often, right? In that specific situation with this specific number of variables and using a quantum algorithm in a classical machine, which are a big HPC cluster, we were able to improve the speed up of the classical equivalent classical solution. That's not quantum advantage, right? There are some cases that are very, very promising, and I'm very excited that some of them are making great progress. But today we still don't have that practical use case that actually give us that advantage. And I would love to, but but it's not the case. To me, quantum chemistry is probably one of the most promising fields because it's the perfect fit for a quantum computer. At the end of the day, a quantum computer is a quantum system, the same as a molecule or a complex molecule. And there are many problems in nature that we haven't been able to figure out yet. And if you allow me, I'm going to spend just 1 minute to explain one of them that I particularly like very much. And it's the production of ammonia. And ammonia is a very single particle. It's very simple particle. It's just nitrogen and 3 atoms of hydrogen, so NH3. But it's very difficult to produce by us humans. We know how to do it, but we have to put incredible pressure and very high temperatures, like over 500 degrees Celsius, in order to produce ammonia. Only that reaction is responsible for 2% of the entire reaction of all the energy reactions that happen in humanity for industrial purposes. It's ridiculous. And we have this small microorganism, the cyanobacterium. It's a little bit, is a single cell that when you drop it in the right medium, is able to produce ammonia naturally at room temperature. We don't know why or how that happens because it's a quantum process that we do not understand. When we were able to create a quantum computer and map all the variables that are relevant in that reaction, we will be able to make the production of ammonia much more efficiently. And this is a big deal because ammonia is basically what is used for all the fertilizers that feed the entire global population, right? Is very important for the food chain. So yeah, the floor is open to try to improve those algorithms and the technology that runs them.
So we are getting close to the end of this panel. So as we are concluding this panel, what advice would you give to individuals or organizations that are looking to get involved to the quantum technology space?
Well, to individuals, I'd say that we are focusing students mainly, right, or people who are entering their career paths. What I would suggest is go look into the job offers, right, and the postings that you can see on LinkedIn and things like that, and you can then see what quantum companies, quantum startups are asking for. Right, and then you can learn to use those. If you already know how to program in Python, say for instance, then just do one of these IBM courses, and then maybe you'll be prepared for one of these jobs. Right. If we are talking about corporations, then it's a little bit different, but it's not that different in the sense that maybe getting a lot of people right now is not as essential, right? But you should have people on your company already focusing on quantum computing, right? And one of the things that you could already do is start to train your internal teams, right? Data scientists, machine learning engineers, and things like that on the basics of quantum computing, so that they are ready when this revolution comes in the end. So that's what I would say as a suggestion for.
Okay,
yeah.
let's Juan, and then we'll finish by Antonio. Juan, what is your take on that? What do you suggest?
Recommendations for people or for companies? Sorry, I didn't grab the
Both.
question.
Both.
Okay, so for people, I would say in general, stay curious. And if you stay curious and learning about, you are really passionate about this technology, the rest will come by itself. I didn't know anything about quantum mechanics or quantum technologies 3 years ago, and it was such a fascinating technology that it's been like driving in a motor ski since then in terms of the amount of knowledge that is out there. Companies will notice that. You can formalize your knowledge by doing things by yourself, publishing things in your GitHub pages or any other platform where you can expose your work to show the world that you really care, writing blogs, whatever that is. And the companies will discover you because, as everyone was saying today, there is a gap, there is a need of that talent, and we cannot afford to wait for the next generation of PhD in quantum mechanics to get out of university, right? If I have to give an advice to companies themselves, to big enterprises, I'm going to advocate for my own field, that is quantum networking, because quantum computers are being developed and we don't have one yet. Quantum networks and quantum cryptography work. It's working today. It's something that you can start considering and adopting, because at some point the cryptography as it is known today is going to be invalid, and that time you want to be ready and have a plan B for that.
Antonio, thank you, Juan. Antonio?
For organizations, I will say that don't fear the quantum. Don't fear the quantum, because there are a lot of companies that helps you to go into the quantum world, to adapt or to adopt the quantum technologies. So if you don't want, you don't need people that knows about quantum. You could hire another company and just have an agreement and just use is as easy as it sounds. You don't need, of course, if you are a big company, of course you need some quantum team, of course, but for small companies, you don't need, you only need to find a company that solves your use case, your business problem, and another company, probably another company that integrates that solution in your workflow, and just use it for people. Quantum is a very exciting world. It's a world that have physics, that have maths, have business. They're out of different roles here in the quantum world. Probably people that know about a lot about physics, they don't know how to program, but they are building quantum computers. We have a lot of providers in our company that they don't know how to program, but they are building quantum computers. You don't need to know anything about physics if you want to program, and you don't need to know anything about program or physics if you want to integrate your quantum solution in your company. So there are a lot of different rules. Find your own path and enjoy.
Thank you very much to all of you. Please join me for a round of applause for. And now, if you have questions, I will pass the microphone.
Thank you very much for the presentation. It has been really, really interesting and very educational for me. I have a background in master, in data science. So I'm kind of curious about the use cases you've been mentioning. If you could get a little bit deeper on why quantum is better than the standard approaches, that'd be much appreciated.
We have a concept that is what we are calling the quantum business advantage. Quantum business advantage is not the quantum advantage, is if quantum computers now, if you can reach quantum computers and you can solve your problems in a better way than your own resources can do. You don't need to send your problems to the HPC in Barcelona, or okay, you have your own resources, you have your own people, you have your own clouds or something like that. So compared to that, probably quantum is better than what you have if you are in a small company. But for big companies, they are out of different problems that are related to, for example, risk. What happened if your company of your competence start using quantum computers? Quantum computers gain some advantage. They are starting to lower the prices, and all your clients go to your competence, to the other companies. What happens? You need to, if you are a big company, probably you need to be prepared to the quantum world. Probably not, you don't have any use case now that using quantum will improve the performance or the accuracy of your problem. But if you want to start using quantum for hedging your risk, now is a very good moment. In the future, if you want to do probably in next 5 years,
It will be too late.
It will be too late. You will need 1 year to integrate all the things and to experiment, to find the proper provider that helps you to build the algorithms, and when you finish the process, you don't have clients.
Again, I'm kind of interested in trying to understand the use case, right? So let's say we are talking about this routing problem. You're saying the difference of doing it, let's say the quantum way and using the standard way, is modeling the uncertainty on the parameters, or what is the big difference on? I'm trying to understand.
For a routing problem, there are out of different algorithms that are well known. For example, the TSP. TSP is a very well-known algorithm, the travel sales person problem. This is NP complete. This is very hard to calculate, very hard to find a good solution. So with quantum computing will help you to find the optimal solution for that problem. If you own only a car and you have to go to 5 or 6 places every day, you don't have problem. If you are the owner of a very big logistic company that have, I don't know, 1,000, 2,000 trucks to move every day, imagine the amount of petrol that you are going to save.
It's for combinatorial problems that it is.
Yeah, this is a use case.
Dimensions. See, classical computing take years, and I'm not sure that you will have the answer. Yeah. But the quantum computing allows you to have to solve problems that have a lot of complexity, and logistics is one of the way to do that. But let's ask to the expert in logistics, Juan.
All right, I'll put my hat of experts in logistics if you give me that title. The problem with the travel salesman and other optimization problems is that you basically are mapping your problem in the quantum computer in the topology of your qubits. That's another way to solve it on top of what has been mentioned already. There is what is called an adiabatic way to do it, in which basically I create my quantum state and I map the nodes of my problem, in the case of the travel salesman problem, into the different qubits, and then let the machine to reach the lower energy state naturally, and do it multiple times to that statistically significant result that I'm looking for. And the lower energy state will give me naturally the solution to my problem. That is the theory. But again, these machines are not perfect, and you will not be able to do something that you cannot achieve with a regular HPC cluster and a lot of computation capabilities today. However, the algorithm is very promising, and as soon as we have more powerful quantum computers, we will be able to achieve speed ups over that problem. It's a very promising field.
Okay, another question.
Great presentation. I have a question about post-quantum resistant algorithms. I understand right now that we're using RSA algorithms to save the servers and other things, but using harvest now, decrypt later, and using quantum computers, we can decrypt with a quantum computer any RSA algorithm. Also, blockchain like Bitcoin, the elliptic curve can be reached through quantum computing. So I would like to know what options do we have with post-quantum resistant algorithms? Thank you.
Excellent. Yeah, happy to elaborate on that. That's one of the most common use cases for quantum computers. Quantum computers are very good at factorization of numbers. If I give to a classical computer a 3 and a 5, it will give me a 15 like this immediately. If I give it a number 15 and I tell the classical computer, give me the 2 prime numbers that make this 15, it's going to give me that 3 and that 5 as well as a solution, but it's going to take a lot more time because the calculation of that factorization is exponential in complexity. Today's encryption, like RSA, is based on factorizations of very long numbers, in particular 600 plus numbers that you have to decompose in the prime factors in order to get your private key and your public key. That is a big risk today because as you were saying, I can start gathering data, save it there, it's all encrypted, I cannot read it. And when I have a computer that is able to crack that factorization problem, I can start decrypting my data and have access to it. What are the solutions to that? We have two solutions, the software-based, let's say, solution with cryptographic complexity, or the physical solution using quantum itself. For the first one, we can create basically more complex mathematical problems that, for example, IES 256 or these new algorithms like Kyber that are being evaluated right now, those are post-quantum cryptography algorithms. There is nothing quantum in post-quantum cryptography algorithm. It only means that I'm using not only factorization of numbers, but in the case of Kyber, for example, factorization of polynomials that make a problem so difficult to resolve that even for a quantum computer, it will be impossible to crack and decrypt that data in a reasonable amount of time. On the other side, I have the physical implementation that we were mentioning before with quantum key distribution that can work in combination with PQC. Means that I use particles of light to create my key, and in that way, I do not depend on mathematical complexity anymore to break encryption. I can use the properties of quantum computers, for quantum mechanics themselves to encrypt my data. I hope that was clear.
Crystal, is there any other question? Yes, please. Please go ahead. A moment.
I guess I've been reading about quantum and trying to understand exactly what that entanglement meant. And is it just based on the polarization of light? That's my question. Is it based on the directional polarization of light when you talk about the light particles?
No, you can have entanglement on any, say, quantum mechanical property. So for instance, the simplest example is you have a neutral particle, which is called a pion. This pion is at rest, and then it suddenly splits into an electron and a positron. That electron and that positron are entangled together, and they're not particles of light. So you can have electrons entangled, you can have photons entangled, you can also have, for instance, the superconducting devices that we were talking about before, that IBM is developing, for instance, or that the people at Amazon are also developing, as Juan was saying. These superconductors, the superconducting qubits, are not electrons themselves, but some kind of, if you like, synthetic qubit. Is like you have an emergent property of those things, and those big things, which are not elementary particles, can also get entangled. So you can get entanglement as long as you have two quantum things together interacting.
Hope that it was clear. Any other question?
I'm gonna keep asking about use cases. Sorry.
That's fine. That's fine.
Can get a little bit. Oh, go ahead. Sorry.
Yeah, I have a lot of use cases in our platform. So
If you want to talk a little bit further about the NH3 problems, that's interesting as well.
So we are going to show some. Excuse. Could you?
yeah,
Okay. We are going to show the platform of QCentroid that will give example use case that they have with their clients right now. So to be able to illustrate, because it could be really theoretical, a theory, all of that, talking about quantum, generally speaking. But here we will have something concrete. We thought about giving you, before leaving, an idea of what exactly we are doing in the quantum world.
this this is our product. So
Do you see anything? Oh, hold on. We have the technical. Yes, maybe. This is the problems when you have a live demo. It's always happening. So actually, you have the owner of the brewery that is Trent, that is online. I met him last week, and he explained to me his problems, that it's really hard for him to find a solution now to mitigate the rising cost of the brewery. Okay, so we are on the use century platform, Antonio.
here's our product. We have for every kind of user, from the no experienced user that only wants to adopt or adapt their workflow to their own company. We have different tools for companies that they don't want to know anything about quantum. They don't want to. They have business use cases and they want to solve that only.
So, for example, could you show us an example from one of those guys? Not the credit risk, because I know it's something really boring. I can tell you guys it's really boring. Something that could be interesting, yeah. Asset diversification, perfect.
For example, that you want to invest some money, for example, and you have different options, and okay, there are the different approaches that are market with portfolio optimization or things related to covariance, but well, this is a use case for one big company that they have a lot of different investment possibilities, and they want to invest only in 50 or 60 assets. They have access to 1,000, 2,000 assets. So with this algorithm, for example, that this algorithm is running in a quantum computer, you could extract from your 2,000 asset portfolio, you could start, for example, 50 or 60 assets that are not correlated. And you will find the biggest uncorrelated subset of assets. So you can invest without any kind of correlation. Correlation is sometimes helpful, but sometimes it's not helpful in the finance world. So what we are offering, okay, if you are a business manager, you go inside, you can find that there are business descriptions, some kind of graphical support. Here there are a lot of different information about why do you have to use quantum computers instead of classical computing. the input that this problem wants to or accepts, the output, okay. For the business manager knows the problem, knows, and okay, let's choose that. So we'll go to here, you pass this problem to your technical guy. We have a lot of different tools to integrate in Salesforce, in Google Cloud, and whatever. We have a lot of different. So you have to extract your data. When you have your data, you put your data here in Concentrate. This is the web page. We are thinking you have to use the web page only once to see that okay, everything is working, and you have all the stuff that you need. But in the future, we will integrate this platform in your workflow. So we have an API, we have some Python library, we have a lot of things to integrate. We have also some connected with different platforms, different providers. So, okay, this is only the use case. We have some kind of simple data about, okay, if you go to, you know that, okay, you see at the bottom that there are a lot of different, for example, here, there are a lot of different assets. For example, the IDX 35. We have here, we have three algorithms for that problems. You could input your data. We have this text box with a simple input. So you want, you could execute, you press execute. We have the problems of the asynchronous quantum computers. So I will show you what happened with Dennis.
So if I understand well, here you have a presentation of your problem. You can input the data that you want, and you can choose the algorithm that you want. You execute it, and you have the result. Am I correct? Yeah. Okay.
We have a lot of different algorithms running because of this synchronous problem, but you could test. This web page is only for testing.
Okay.
Ideally, if you arrive at Concentrate, you will see your use case with 4, 5, 6 different algorithms with different technologies and different providers. So you need to test which combination of technology or hardware and provider is the best combination for you.
So it's a marketplace, basically. It's a place that I have algorithm and I have provider, and I choose. It's a market. It's a Mercadona of the quantum. If I... Okay.
The other thing is big companies, we are offering this platform and just because we have connected with every kind of quantum hardware. We have a lot of development in terms of security, compliance. We have regulatory approval for working for US banks. So we have a business-ready platform that you could install in your own cloud, and you could start using the platform. For example, we have a very big client that is top 10 in the finance world, and that they have their own instance of Concentrate, private. They have different agreements with different algorithm providers. For example, one is Multiverse that I mentioned before. It's one of the biggest quantum startups. They have. So all these providers are publishing their own algorithms in their private instance. and their employees of this company or their clients of this company could use their own algorithms. So we could offer a lot of things that probably you couldn't see here, but this platform is secure. We have a lot of regulatory checks. We have a lot of different things to assure that is a platform business ready, but it is only for big companies. So,
Sorry if I may interrupt you. This is basically how the industry works. So basically, there are publishers of algorithms.
yeah. Here the
And
problem is that in the quantum world, there are three different actors. One is the quantum hardware provider. The quantum hardware provider are often people from physics or chemistry that they know how to build quantum hardware, but they don't know anything about cloud access. They don't know anything about how to sell. They don't know how to sell the quantum time of the quantum computer. They don't know how to sell. There are another actor that is the quantum algorithm provider. Probably most of them are from universities, are maths or computer science. They know how to build algorithms, but they don't know how to sell them. So we have a lot of agreement with companies from almost every country in the world. We have, I think that we have 40 countries now with different agreements that they want to publish their own algorithms to sell to sell the algorithms in the platform. So we offer them a lot of different use cases. They choose the use case. They build the algorithm. They publish. We reach an agreement on the price. We start selling. So every client of us could go to the platform to see the use case and will choose from the list of the providers. Will choose which is the best provider for him. But if you want to test with different input data, with different hardware parameterization, that is one of the features that we are going to publish in the next week. We could experiment with different options, and when you are happy with the result, you choose and you integrate with that provider, that computer, and that recite of hyperparameters of the quantum hardware, and with that, you could integrate in your workflow and start using on a daily basis.
Okay, thank you very much, Antonio. We are. What I suggest is, if anyone wants to have the list of all the use case that Qcentroid has, you know who to contact. He will. I'm sure Antonio will be around here, and you can contact him. We are close to the end of this event. I would like to first take the time to thank ICAI for giving us the opportunity to be in this facility. Thank you very much for that. The MIT Club of Spain to organize this type of event, trying to promote more and more the technologies that are not that known by everybody. I would like to thank all the panelists, Antonio, Alvaro, y Juan, que está, that is. Usually I speak 3 languages on the same day, so I don't know, I can switch on. Sorry about that. So I would like to thank Juan and Mike that left us for this outstanding presentation. I hope that at the end of this event, you have been able to understand a little bit what is quantum computing, what it can bring in your life, and what you have to be to have attention on. Thank you very much to everybody, and a final round of applause for everybody.